So here's section 7.3 on conservative and non-conservative forces. Our objectives here are to define conservative and non-conservative forces and correctly apply problem-solving strategies to each one. We want to be able to use conservation of energy to solve some problems, including those types of problems that may involve friction. In the last section, we showed that mechanical energy is conserved in a system where the force of gravity acts between objects in the system. And this is true for all conservative forces. Remember, mechanical energy is both your kinetic energy and your gravitational potential energy. And these two things would be conserved in many situations. Now, conservative forces are those forces where the mechanical energy of the system is, in fact, conserved. So, for example, gravity was a conservative force. Basically, this means that there are no transformations from mechanical energy to internal energy or heat. Now, a couple of important points about conservative forces. The work done by a conservative force is independent of the path followed by the members of the system and depends only on the initial and final configurations of the system. So when we talk about work done by this force, what we're saying is it doesn't matter how you get from point A to point B. If we have point A over here, point B over here, you could get to these 2 points by a direct line. You could get to them by following a curvy path. You could get to them by maybe following a staircase. Whichever way you choose to get from A to B, it doesn't really make a difference in the work done by that conservative force. Also, the work done by a conservative force when the object is moved through a closed path is going to be equal to 0. So running around a track, for example, and ending in the same exact spot that you started from is going to be a place where you have 0 total work. Again, these are things that are true for a conservative force. So what other forces did we talk about that would be considered conservative? Take a second, think about it. You got it. Springs. Springs are also going to follow these two guidelines that we stated here, that the work done by that conservative force is independent of the path, so it doesn't matter how you get from stretched to compressed or whatever that might be. It just looks at those initial and final configurations of the system, and when you look over a closed path with a spring, the total work done would be 0. So, when we go back to last chapter, chapter 6, we talked about work and explained those things. We talked about how stretching a spring from equilibrium to some x max and said that the amount of work that would be done would be this 1/2 kx max squared. Remember, we got that amount of work by realizing that the AP physics definition of work is the integral of the force, where with springs, the integral of the force is an integral of kx. So that's where we got the 1/2 kx squared. Since there's no change in the kinetic energy in this amount of work, the change in the potential energy must be what's going on in this sort of a case. So when we look at springs, there is an equation for the change in the potential energy of that spring, where that potential energy is a 1/2 kx squared. And this didn't show up very good when I downloaded this, so we'll just rewrite it here. 1/2 kx squared is our potential energy function for a spring that would follow Hooke's law. So we define this as elastic potential energy. There are many forms of potential energies. Any sort of energy that's being stored in some way would be considered potential. So it's not just gravitational potential, but there's also elastic potential and chemical potential. But that elastic potential is going to be the energy stored in a deformed spring. And since it is proportional to the x squared value, like you see in this equation that we completed here, that elastic potential energy is always going to be a positive value, whether you have a spring that is stretched or compressed. Now let's look at non-conservative forces. A non-conservative force is a force between objects in a system that does in fact cause some sort of transformation of mechanical energy to internal energy. Basically, the movement of this object is resulting in some sort of heat being generated. These would be problems that are involving friction. So imagine that you have a block that's initially sliding on a table, and eventually the block would come to rest, right? So here's your surface, you start the block over here, you get it going in this direction, eventually this block is going to slow down and stop. It has some initial kinetic energy, but by the time it gets to that stopping point, it would have 0 kinetic energy once it is stopped. Now clearly, when we place this on a horizontal surface, there isn't any change in the gravitational potential energy, or really any potential energy for that matter. So what is it that has changed in this system? The answer is really just the temperature of the surfaces. The frictional force that would be present between that block and the surface would create friction and cause some of the mechanical energy that you started with to transfer into internal energy or heat. Now remember that the two requirements of a conservative force is that the path taken does not matter, and the work over a closed path would be equal to 0. So basically we'd be saying when we have the block here going from point A to point B, would it matter how we got there if we took a straight line path versus a curvy path? If we had the block move in a closed circle, would there be 0 total work done? Do any of these things really hold for friction? And as we think about that question, that answer would be no. Neither one of these hold for friction. If we were to take a curvy path instead of a straight line path, there would be more energy that went into heating up those surfaces or internal energy from friction. If we were to slide the block in a closed circle or around a loop that way, there wouldn't be 0 work done. This would have an increase in the internal energy. So remember that the result of friction is an increase in that internal energy. And an increase in internal energy had to come from somewhere, so it's really coming from a decrease in the kinetic energy as this block slides across the table. Now that we have potential energy that's also being considered in some of our problems, we could say that any increase in internal energy has to be the result of some sort of decrease in mechanical energy. Basically, we have this give and take situation going on, that the internal energy had to come from some other form of energy. So now we have our most general form of the continuity equation, which says that if there's going to be any change in kinetic or potential energy, or any change in mechanical energy, that change is going into the internal energy of the system, or that frictional force multiplied by a distance that this object is sliding across that surface for. Or another way to put that is to move this term just over to the other side of the equation, and we have K plus U plus that internal energy equaling any sort of change in the system, which should end up being a 0 total change. This is essentially what we mean by conservation of energy. Now, remember, when we place that K in the equation, that K could be the kinetic energy from several objects in the system. It could be many pieces of that system that are moving. And the U in this equation can be the potential energy of many different types. It could be gravitational potential energy or maybe elastic potential energy. But essentially what we're getting at here is this conservation of energy theory, that anything that has a change in its energy is really coming from somewhere else, so that the total energy of kinetic, potential, and internal of an isolated system is going to be conserved, regardless of whether the forces acting within that system are conservative or non-conservative. There is no violation that has ever been observed in this. Basically, when you look at all the different energies in a system, that total has to be a constant. Now, when we use energy to solve problems, there's a few problem-solving strategies that can be helpful. One is to begin by defining in your system a reference point. So if you have maybe a problem with a building and a person that might be standing next to that, you need to decide where are you going to call 0 potential energy. Oftentimes people might choose the ground level to be 0 potential energy. Other times you might want to choose maybe the top of the building to be a 0 potential energy level. Anything in your problem could be considered a reference point for potential energy. You do have the freedom to choose where that point is going to be. Choose a spot that's going to make the problem the easiest for you to solve. Point number 2, determine if energy transfers occur across the boundaries of the system. If there is some sort of transfer, then the sum of those transfers have to equal the change in the total energy of the system. If there's not any transfers, then the total energy in your system has to remain constant, and the total change would now have to be equal to 0. The next point here is to create expressions for each object in the system for potential and kinetic energy. Basically, make sure that you're adding up all of the energies present in your system. Determine if your mechanical energy is going to be conserved, and set the initial equal to final. If you have friction present in that problem, however, mechanical energy would not be conserved. Total energy still would, but mechanical energy would not be conserved, since some of that mechanical energy might go into internal energy or heat. And lastly, of course, check your answers and make sure that they actually make sense once you've come up with a final answer.